Hello friends, welcome. Today we will discuss with real numbers. The section is Euclid's division algorithm and Euclid's division lemma. So before we start the Euclid's division lemma, first we discuss about the real numbers. When I asked a student what is real number, everyone say 1, 2, 3. But real numbers is a big word. Look at this picture. First, real numbers first when the real number starts counting, it is 1, 2, 3. So here we said is called set of natural number or counting number, because if you want to start the counting, always use first object is 1, then 2, then 3. But we feel the 0. So including 0, the word now is we use the set of W. W means set of whole numbers. But if you do the operation on natural number or whole number, only you can plus, that is addition possible. Any to add in a natural number, if you add, you get a natural number. Like 2 plus 3 is equals to 5. 5 is a natural number. But if you multiply 2 3 is 6, that is also a natural number. So addition and multiplication are closer operation. But if you think the division, suppose 2 minus 3 is equals to minus 1, but it's not belongs to natural number. So division is not a closer operation. So what to do? So we have to extend our number system and see the next block, that is called set of integers, or I, or we denote Z for this one. Here we put all negative numbers, minus 1, minus 2, minus 3. So natural number, whole number and set of negative numbers. So this is the set of integers. But again we have some operation, that is, addition is an operation, subtraction is an operation, multiplication operation, and division another operation. But if I take 2 divided by 4, the result comes half. But this half is not included in set of integers. So we extend our number system and includes all type of numbers which are on the form p by q, where p and q are co-prime integers. What are co-prime integers? Co-prime means they have no common factor, like 3 and 4, 5 and 6, 7 and 8, they are co-prime. So all natural number, whole number, integers, positive integer, negative integer, and all the fractions, all the numbers which contains minus 2 by 3, that is in the form p by q, all the numbers 3.5, 2.5 in decimal, or 1.3333, that is a recurring decimal. So all these numbers we include in p by q form. And these decimal numbers 2 by 5 we can express in the form p by q. 1.333, so this is equals to 1 by 3, and this is in the form p by q. So these are all rational numbers. But some numbers are in the number system which are not rational, they are irrational. See, in this block we have written root 2. Root 2, root 3 you cannot express in the form p by q. That's why we are taking these numbers in another block and we show these are set of irrational numbers. So rational number and irrational number is a combination, and we got set of real numbers. Now we'll discuss the Euclid's division algorithm. Yes. Now, Euclid's division algorithm, when you divide 6 by 3, you will get 0. If you divide 7 by 3, you will get remainder 1. If you divide 8, 6, remainder 2. If you divide 9 by 3, 3 is a 9, remainder 0. If you divide 10, it is a 9, remainder 1. So what you observe, here the remainder is 0, then it is coming 1, then it is 2, then it is 0. So after 2, again it come back to 0, 1, 2. So this way, when you divide any number a by 3, 3 is the divisor, and we get a quotient like 2 or 3, and we get a remainder r. Here r is equals to, r may be 0 or maybe 1 or maybe 2, and these all numbers are less than divisor 3. So now we'll do the statement of this one. Yes. Now what is the statement of this Euclid's lemma? Given positive integers a and b, there exist two whole numbers q and r. So we can write this like, we are taking a here, a that is here, and we are taking b as divisor, and we get quotient, and then we get remainder, and we know that dividend is equals to divisor into quotient plus remainder. So this is the division lemma. A is equal to BQ plus R, where R is the remainder and R is greater than equals to 0 but less than the divisor B. Now discuss example. Yes. Now see, so that any odd positive integers is of the form 4q plus 1 or 4q plus 3. So first we will take any odd positive integer. Let A be any odd positive integer. And here we take B, the divisor B is equals to 4. So according to the Euclid's lemma, we can write A is equals to 4 into quotient plus remainder, where R is equals to 0, 1, 2, 3, because R is greater than equals to 0, less than equals to 4. So therefore A is equals to, A may be 4q when R is equals to 0. A is equals to 4q plus 1 when R is equals to 1. A is equals to 4q plus 2 when R is equals to 2. A is equals to 4q plus 3, when r is equals to 3. Now the first one, a is equal to 4q. It is an even number because it is a multiple of 4. Second one, 4q plus 1, and this is an odd integer because 4q is an even integer plus 1, or you can write it as 2q plus 1 is equals to, as it is a plus 1, even number plus 1, so it is an odd number. Odd integer. Now the third one, 4q plus 2, and so it is divisible by 2, so it is an even number. The fourth one is, we can write 2q plus 2, 1 plus 1. So this portion is divisible by 2 and remainder is 1. So there again it is an odd integer. So thus we got a is equal to 4q plus 1 is an odd integer, and another one 4q plus 3 which is an odd integer, and so our question was you have to prove 4q plus 1 and 4q plus 3 are odd integers, and that is proved. Thank you.